Well, thank you for coming, everyone. I'd like to give a short introduction to Marco. So let's begin by acknowledging the traditional owners of the land we're using today, and we pay our respect to the elders past, present, and emerging. So Marco is a professor at the University of in Rome in the Department of Economics and Finance, and he held a position at SUTD in Singapore, Associate Paris, University of Torino, University D'Annunzio, University of Roma La Pienza, and University of Palma. He holds a laureate in economics and social science at Bocconi University, and HDR in applied mathematics from the University of Paris. So Marco has made a really important and fundamental contribution to a variety of topics in game theory, applied probability and social learning. And his works has been highly cited and published at the most prestigious journals in economics and operations research. He currently holds seven editorial positions, including one being the area editor of mathematics of operations research. So thank you, Marco, for being here, and look forward to the talk.
Thank you for this presentation. I'm embarrassed. Should I use the microphone or?
Yes. Yes, please.
Will. Sorry. So thank you so much for this invitation. This is not really a talk on optimization. It's more a talk on some tools that can be used in decision theory. There's no part on optimization, but you know, it's very instrumental to This is a joint work with my long-term co-authors and friends, Alfred Müller in Siegen, in Germany, Ilya Sedlin in Seattle, in Singapore, and Bob Winkler at Fukuoka Business School in Dura, in the States. Okay, let me spoiler my own talk and tell you from the very beginning what I am after. You're dealing with multivariate stochastic dominance. Don't be afraid, I will explain what it is. And we will be looking for sufficient conditions. Moreover, we will be looking for sufficient conditions that depend only on the marginal distribution of the distribution of the problem. And to do that, we start by showing that if we do things in the classical setting, you know, if you consider, you know, the classical first order stochastic dominance, again, I will explain what this is. We are bound to crash very hard on the door, against the wall, because for reasons that we see. So to overcome this problem, we will turn to what has been called for a number of years now, almost stochastic dominance. And once we go to almost stochastic dominance, there is a chat. Should I? Okay. Once we turn to almost stochastic dominance, we'll see that it becomes doable to find sufficient conditions. Okay, so okay. Not too much. Okay. So what is stochastic dominance? Stochastic dominance is about comparing two random vectors. We are doing multivariate, so we go straight to random vectors, x and y. There could be the return of two different portfolios. X is one portfolio with n elements, y is another portfolio with n elements. Imagine you know, the portfolio being composed by similar securities, and you want to compare their return. We have seen the x as a distribution function s, Y is a distribution function G. This will go throughout the talk. And the corresponding marginals are Fi and Gi. Fi for the marginals of X and Gi for the marginals of Y. And so take a class U of functions, U, small u. The reason for the term, for the symbol U is that typically these are utility functions. In the classical form models expected utility framework of decision theory. And we say that X is dominated by Y in this order determined by U, by the family script Q, if whenever you consider the expected utility of X with some utility U and the same expected utility of Y with the same utility U, the one of X is smaller than the one of Y, no matter how you choose small u in this class, big U of utility functions. So in particular, you could choose script U to be the class of all increasing functions. So the class of all increasing utilities is the class of utilities that represent the preferences of decision makers who prefer more money to less money. So no issues of risk aversion here, no nothing, just rationality. More money is better than less money. Okay. And when this is the case, when Q is the class of increasing functions, so we say that X is dominated by Y in the sense. There are several characterizations of stochastic dominance, of first order stochastic dominance, and these are, the most well-known of them. So let's very Y in the sense that I just said, if and only if I can couple X and Y, namely I can find copies of X, X tilde, and of Y, Y tilde, that are on the same probability space, such that X is smaller than Y or more sure. So this is the first characterization, which is very useful per se and to compute things. The other characterization, and I can go from X to Y by transferring probability mass in an increasing sense. So I transfer probability from smaller values to higher values. Okay? And again, this is a characterization, namely every time X is more than Y in the sense of stochastic dominance, I can go from one to the other with this transfer. And the last one is that if you take the class of upper sets, an upper set is a set that if X is in the set and Y is larger than X, Y is also in the set. For the class of upper sets, the probability of X being the upper set is smaller than the probability of Y being the upper set. So Y tends to be the higher probability in the region where values are high. So these are characterizations. Each one of them is equivalent to all the others. And if you go to the univariate case, these characterizations are actually handy, especially the last one, because the last one translates into this. That if you take the distribution function of X, F, and you compare it to the distribution function of Y, G, point-wise, F is higher than Y. So Y tends to be on the right of F. And this condition is very easy to verify. If you know the distributions, you can compute the distribution functions, or at least numerically do it. You have to just to compare to the two distributions to verify whether stochastic dominance occurs. Now, the fact that this is easy to verify doesn't mean that it's satisfied easily. In particular, if you take two normal distributions, what's feasible with the two normal distributions, and say that X has a normal distribution parameter mu and sigma squared, and Y has a normal distribution parameter u and tau squared. Well, X is dominated by Y, and if the mean of X is more than the mean of Y, and that's reasonable. But what surprising for people who haven't seen this things before, is that the two variances have to be the same. So if you have two distributions that are normal and they have two different variances, even slightly different, you cannot compare them in the sense of stochastic dominance. One may have mean 0, the other one may have mean 1 billion. Still, you cannot compare them. Okay, so stochastic dominance is a tricky object. It's difficult to realize it. And when you go to the multivariate case, it's even worse. It's worse for two reasons, because the characterization that in the univariate case was very simple to handle because it required only the comparison of distribution variables. Here is much more complicated because you would have, in principle, to verify the quantity of all of sets, which is not doable. So if you think, well, okay, you just look at the multivariate distribution functions, that's not enough. If you just compare the multivariate distribution functions, you get a weaker characterization. It's not enough. But even if these are easy to verify, which is not, you would have the same problem that we had before, but now even on a larger scale, because if you have x and y that are both multinormally distributed, x is dominated by y if the mean of x is more than the mean of y, okay? But now, not just the variances have to be the same, the whole covariance matrices have to be the same. So not only they have to have the same variances, they have to have the same defined structure, which is almost impossible to have in real life, especially if you don't know exactly the distributions and you obtain them by sampling. Well, forget it. Okay, so this is the issue that you're facing. And finding sufficient conditions for stochastic dominance is not easy. I mean, they are necessary conditions, but the sufficient conditions are quite complicated to get. And when you get them, they're not easy to verify. I mean, I'll come back to this if we have time. But let me go to the possibility. So, given that stochastic dominance is difficult to verify, and even when it's verifiable, usually it doesn't hold. We will go for something weaker. So the idea goes back to a paper by Leshner and Levy in Management Science. I forgot the exact date, probably 2005. They introduced what they called almost stochastics. Okay, so this idea is along those lines. It's not the same, but it's along those lines. So what was the gist of their contribution? So let's go back to what we said before. Stochastic dominance is rarely holds. Okay, take two distributions. Most often they are not ordered in the sense of stochastic dominance. So why is that? That typically, stochastic dominance doesn't hold. Well, that's due to the fact that you're comparing the expectation of a whole class of utility functions, all the increasing utility functions, and that class is huge. There's too much stuff in there. Okay, you're asking for too much. So their idea, and the version of their idea that we consider here is to get rid of the utility functions that are too extreme. What do I mean by too extreme? Well, they are either too flat or too steep. So they have regions that are either too flat or too steep. Okay, so I restrict my attention to a class of increasing utility functions that are a bit less extreme. So how do I do this? I look at the derivative. Here you are in multivariate setting, so I do the function of derivatives in every direction. And in every direction, I want that for every pair x and y, the the derivative, marginal utility in X, is larger than the marginal utility in Y multiplied by gamma, where gamma is a number between 0. So if you want to translate this in a different form, if you compare the infimum to the supremum of the derivatives, this ratio has to be larger than gamma along each direction. Okay, so this bounds how steep or how flat the utility can be. Okay, and according to how you choose gamma, okay, you have a stricter or weaker condition. So first of all, whenever gamma is smaller than lambda, if you have two values of these gammas, these are vectors, but just consider the univariate case for a moment. If gamma is smaller than lambda, then the class of utilities determined by lambda is smaller than the class of utilities determined by gamma. Therefore, when you have a smaller class, it's easier for the ordering to hold. Okay? So when you increase gamma, do I get it right? Yes, when you increase gamma, the thing becomes easier to the ordering becomes easier to hold. In particular, if gamma is equal to 0, it means that you are not putting any constraint on the utilities, so you go back to the usual stochastic dominance. And when gamma is equal to 1, it means that these two have to be equal. Therefore, the only class of functions where the supremum of the is the same are affine functions. So basically, that says that all that you do is to compare the spectral value, okay, and nothing else. You're basically comparing preferences of people who have no risk aversion whatsoever. Just choose based on the spectral value. So as you move gamma, you interpolate between the classical stochastic dominance and a situation where you're really easy to satisfy. So the parameter represents different attitudes towards your risk preferences or your preferences. Okay. Now, if you remember when I characterized the stochastic dominance, one of the characterizations for the second one, I said, sorry, the third one, I said that I can go from S to Y by transferring mass to higher values. Okay, so I have my distribution of X, I move mass to higher values, and I keep doing it until I get to the distribution of Y. So it's a transfer characterization. A similar characterization holds here. And so, first of all, let me make precise what I said before. What do I mean by increasing transfer? I mean that if I have two distribution functions, f and g, with mass function small f and small g, let's say this is for the moment. Okay? G is obtained from f via an increasing transfer. I have two values, x1 smaller than x2, and I move mass from x1 to x2. You see? G has less mass on 1 and more mass on 2. Less mass on x1, more mass on x2. And all the rest remains. Okay, so that's an increase in transfer. Now, gamma transfer is this thing, which is ugly to see, but yes, don't even try. Okay, look at this is much better. Okay, so what's the idea? The idea is that, so in an increasing transfer, I have things only of this type. I go from x1 to to S2. I move eta mass from S1 to S2. Increase. And here I said, well, you know, given that I'm not so strict with the utility functions as I was before, I can allow some mass to go the other way. Okay, but how much? Well, gamma. So if this is 1, this is gamma. Remember, gamma is between 0. Okay, so there may be some transfers that go the other way, but they cannot be as large as the ones that go in the right way. Okay, and that is in every direction. This is one dimension. It goes like that, and it's more compensation the other side. Sense. It could be one that goes like that, with just more compensation the other sense. Okay, but it goes direction by dimension by dimension. Sorry. Okay. Theorem. Take two random vectors x and y. Discrete with discrete distribution. Then I have that x is dominated by y in the sense of this gamma class of utility functions. If and only if I can obtain the distribution of x from the distribution of y through this type of transfers, either increasing transfers or gamma transfers. Okay, in every possible direction. Okay, so this is a nice characterization of this gamma dominance for two reasons. Well, it's interesting by itself mathematically, and also I don't know much you know about decision theory and utility theory. There is a lot of there's been a lot of work in paradigms that go beyond expected utility. Okay, all this theory of ambiguity, mass, all sorts of things. And this characterization is interesting because here, for this characterization, you don't need any utility, in a sense. You don't need to assume the classical von Neumann-Morgenstern paradigm of expected utility. Even if you do, you know, some other, even if you adopt some other paradigm, still this is nice because the gamma transfer characterization is only about probabilities. Probability masses that move here and there. And you can ask, if somebody was not an expected utility maximizer, do you prefer to have this move here and that move here, or vice versa? Okay. Yeah, sure. Oh, sorry, I didn't say it. You know, please ask questions.
Just for curiosity, the lambda is fixed at the beginning, right? So let lambda be between 0 and 1, then
yes, but yes, thank you so much for the question. Yes, in principle it's fixed at the beginning. We'll see how to play with this in a moment. Okay. Because yes, in principle, one approach is to say, okay, this is my gamma that represents my preferences. I have two vectors x and y. Let me check whether they are comparable with respect to lambda or to gamma. Another approach is to say, I have x and y. What is the smallest gamma according to which they are comparable?
because we would like to do it as close as possible as 0.
Exactly. Exactly. That's the idea. And that's what we're doing.
One question. In the finite value theorem, when you have like 4 dimensions, then finite values, does this theorem lead to a computing easily where there are it seems it's hard as well, right?
Yeah. Once you increase the dimension, it becomes I mean, if you look at computational hardness, it's not easy. Even for the classical stochastic dominance, there was an old paper by Kimmeldorf and Sampson. No, Sampson and Whitaker, I guess, where they looked at the computational hardness of the classical increasing transfers, and it was. On top of that, there is a mathematical difficulty. That to go from finite to infinite is not so easy. We tried with different orders with Alfred years ago, and we couldn't do it. We thought that we got the limit. So that's why we stick to discrete. Okay. These orders are defined by transfers according to various dimensions. So you may suspect that it's enough to look at the dominance along each direction, and if you have it along each direction, you have it globally, and it's not true. So this is a counterexample. I don't think I have much time, so I'll skip it. But trust me, the order is more complicated than it looks. So it's not enough to look at the marginal dominance to get the joint. We'll get back to this later if we have. This is the main theorem. Okay, so assume that you have two random vectors x and y, and you know the marginal distribution of x and y. And say that the mean of x is more than the mean. Then, if you take this parameter delta I, which despite the ugly look, is just the median of the mixture between f and g. So if you take fi and gi and the mixture 1/2 of fi and gi, you get a new distribution. The delta I is just the median of this distribution. Then, once you have the parameter of delta I, you can compute these respective values. These are functions of yi, and there's a function of xi. You put the whole thing together, you get the parameter of delta. And then we can prove that taking gamma I equal like that for all possible dimensions give you that x is dominated by y with respect to delta. So answering your question, you can start with x and y, then you compute these things, and you look at the smallest gamma that allows you to compare it. Okay. And the nice thing about all this is that these conditions depend only on the marginal. Why is this important? For many different reasons. There are many situations where you have a sort of clear view of what the marginal distributions of things are. But when you go to the joint distribution, you typically have no idea. And even if you have data, say that you have a distribution of dimension 100, and you have a sample of 1,000. Sample of 1,000 is quite big. So sample of 1,000, you can compute the marginal distribution very precisely. But once you go to the joint, it's extremely sparse in dimension 100. You have 1,000 points in dimension 100. You have really no idea. And second, you may want to have the possibility of comparing situations where the joint distribution, the dependent structure, could be very different. That's why we are looking for sufficient conditions. This is a sufficient condition. It's if this happens and this. What I said before cannot be if and only if. It's just if. So it's a sufficient condition, but the nice thing is that it depends on things that are easily computable, namely the marginal distributions. Now, that was when all that we knew was the marginal distributions. What if we know a bit more about the marginal distributions? For instance, we may know that the marginal distributions come from a symmetric location space family, namely family that characterized by two parameters, a location parameter mu and a scale parameter sigma. So this is normal distribution. Okay, or a multivariate normal distribution, and generally an elliptically contour distribution, namely distributions where if you cut the density, you get ellipses. And so this is a restriction with respect to what we had before. But many of the distributions that are used in real life are of this form. So it's nice to have results for this class. And again, we have something similar. So namely, if for every I, Fi and Gi belong to the same Hi location scale family, then we can construct some parameter based on the marginal distributions only, and we can find the gamma, which is this function of this parameter, that gives me the dominance. Okay, and you can see that these parameters now are easier to compute because I'm using the symmetry of a location scale family. Okay. Yeah.
We assume that we know who mu and sigma are.
Yeah. You know mu and sigma, and you also know the type of location scale family they come from. But thank you for the question. Okay, let me get to this. Assume that you know only the mu and the sigma. You don't even know the marginal distributions. You just know the first two moments of the marginal distribution. That's it. Even in that case, you can look up things so that you find the general, and that function of tau that gives you the gamma that guarantees the value. Clearly, the less you know, the higher will be the gamma, obviously. And the more you know, the smaller will be the gamma. So the stronger will be the dominance. And let me go back to this. This is again about the interaction between marginal and joint. Say that you care only about comparing the marginal distributions. So before I was using the marginal distribution to compare the joint. Now I say, let me compare only the marginal distributions. Again, I can do it. And now I get the parameter gamma, which is smaller than the one that I had before. So if I care only about the marginal, I can say more. But if I care about the joint, I have to care about. Okay. But in any case, this is a comparison of two cases. One is the blue dotted line is the curve for normal distribution. So when we know that the distributions in both cases are normal, and the other one is the case where we know only mu and sigma. And you can see that the gamma, when we only know mu and sigma, is higher, but not much higher. So you can do a pretty good job also when you just know mu and sigma. And this is the parameter of organization. Okay. Let me skip this. I'll get back to that later on. Now, if you remember the way I defined the thing, these transfers were all along the same direction. Okay, I said, I can increase here, and this can be compensated by a transfer in the other direction, provided this transfer is small. Now, so there was no interaction or no possible interaction between being better in this direction and being worse in a different direction. Now we are going to look at this case, where I can see different dimensions of these things, these say portfolios that I'm comparing different dimensions to interact. So now I say, okay, we take the marginal utility, and I want that in every point, this marginal utility be between the parameter beta I and another parameter gamma times beta I. But again, like before, gamma is between 0 and 1. And if this happens for every possible dimension I say that S is dominated by Y if this holds for all utilities that satisfy it. So again, I can characterize this via transfers. Let me skip the formula and go to the picture. So I have a transfer in the good direction here. That's compensated by transfer in the bad direction there. But if this is 1, this is gamma. Okay? And you see, before I had gamma I, now the gamma is unique. There's only one gamma that satisfies that in all possible directions. You have the betas, but the betas don't really matter too much. It's like, imagine them to be prices. Okay? So it's exchange values, but they don't really matter too much. Okay? Again, I have a transfer characterization. So X is dominated by Y, gamma 1. As I said, one doesn't make much of a difference. If and only I can go from X to Y through this type of transfers that I told you. And now we have the analogous main theorem in this case. You see, the thing looks like before. If you look at this part here, on this one, it's the same as before, except that now I am up using these prices beta. I have one single gamma, one single condition instead of one in each direction. And they are of the same type as before by aggregation using the exchange rates, if you want, of the beta. Okay? So this is a situation that's useful where you can actually compensate one dimension with another one. This applies really to portfolios, because portfolios, include securities that can be exchanged at some price, and the betas represent the prices. Okay.
Can I
Sure.
ask about the relationship between all of this and in multi-objective optimization dominance? Is it related? I mean, I think it's different because I think you're talking about two portfolios, not two objective
Right.
functions with this common utility. Right?
Yeah.
It's the same. Alpha dominance would be two utilities.
Exactly.
Okay.
Exactly. I mean, I don't know much about alpha dominance, but the little I remember from reading and attending talks is exactly what you said. You have different utilities for the different components.
Modify your definition of non-dominated to maybe take a worse in one utility, alpha worse, or a better in another, or something like that. Yeah. That's different.
Yeah, but here in the end, you have only so even if the characterization and the definition are obtained dimension by dimension, but still there is a unique utility.
There's two utilities.
Yeah, I wouldn't know how to handle this. It's an interesting problem, but I wouldn't know how to handle. Yeah. No, I think in the old days there was somebody who was doing stochastic dominance in multi-attribute utility theory. Even probably Peter Fish was in the old days also in that, but I'd have to look back. Thanks. Okay. So, just to give you an idea of possible application that we have in our paper, one of my co-authors, Dr. Miller, the past few years now, has been dealing with energy problems, and he had data, some data, and so he came up with this idea of comparing, saying that we want to compare setting up a photovoltaic plant in either Siegen or Rome. He's in Siegen, I'm in Rome, equal. And yeah, let's see whether it's more convenient to do it in one place versus the other. I mean, clearly it seems to be more convenient to do it in Siegen, at least if you look at the sun. So these are data, and this is the mean for Siegen and for Rome. Okay, this is the same. As you can see, in Siegen, there is much less radiation. This is the average between 4 a.m. to 10 p.m. in both cities throughout 2020. So it seems to be a no-brainer. But if you try to do it in terms of stochastic dominance, well, you cannot compare these two cities. Why? Because Siegen is north and Rome is south. So in the summer, the days are longer in Siegen than they are in Rome. So at the beginning, especially at the end of the day, there's more light in Siegen. So there's more radiation in Siegen than there is in Rome. So if you say, well, let's compare these two possible investments with respect to stochastic dominance, you cannot do it. But let's see what we can do with our approach. So first of all, we split the day into hours, 17 hours, because we don't count the hours in the night. And we do it for Siegen X and for Rome Y. And we have a random vector Z, which describes the consumption. We can see this as some sort of background risk. Okay, so we have prosumers, as we say, namely households that on one hand consume electricity, and on the other hand produce electricity because they install solar panels on their roof. Say. Okay. And we can say that you can buy electricity at a price beta, and when you have excess, you can sell it. But when you try to sell it, you don't get beta; you get a lower price. You get gamma times beta. Okay. And you can define an operating policy. The simplest operating policy is that you sell electricity only when production exceeds consumption. Okay? That's quite simple a policy. So we put all these things together, and you get this function. This is what. So when the production is more than the consumption, you get beta, you pay beta, and this is what you get vice versa when the production is larger than the consumption. The consumption is random, so you take the expected utility. With that utility function, the bounds on the marginal utilities are exactly gamma, beta, and beta, like in the definition that I had before. And so if you have an operating policy of that type, you get the x is dominated by y with these parameters gamma and beta that are determined by the prices. But that was just one possible policy. The prosumer could decide, well, let me optimize and choose the best optimal policy, whatever that is. We don't know what that is, but take the best optimal policy. Then you get this as criterion, choice criterion. You get a soup with respect to all possible policy of this. But now the policy itself could depend on X, would depend on the random vector. So this is not an expected utility anymore. Nevertheless, by using our criterion, you can say that even under this choice of policy, so we are beyond expected utility, you can compare the investment in X with the investment in Y. So this really goes beyond expected utility. Sorry, I was a bit fast. Thank you so much.